The previous lecture concentrated on the move instruction and various pic24 addressing modes. This lecture will branch out and begin talking about other pic24 instructions. We'll start out with the add instruction. This form of the add instruction is a register-to-register form in which we'll take one working register, add it to another, and store the result in a destination working register. Any of these operands can be one of the 16 working registers, W0 to W15. Let's take a look at a couple of examples. Here we're going to add W0 plus W1 and stick the result in W2. We don't have to use different registers for all these operands. In fact, we could use the same register. So here we're going to add W2 plus W2 and stick the result in W2. This is the same thing as multiplying W2 by 2. Finally, there's also a byte form of this. In this case, we're going to take the least significant byte of W0, add it to the least significant byte of W1, and place the result in a least significant byte of W2. Let's take a look at some numerical examples. Here we're going to add W0 plus W1, place the result in W2. W0 has this value in it. At the start, W1 has this. If we add these, the result would be A60D, which will be written to W2. Here we're going to do the byte form of this. Notice that we're going to take the least significant byte of W0 and the least significant byte of W1, add those, get this result, and notice that the result, which is placed in the least significant byte of W2, only affects the least significant byte of that register. Finally, here's an example of using the same register for all three operands. This will simply take W2 value, add it to W2, stick the result back in W2. At this point, we've modified the value of the W2 register. So if we can do addition, we can also do subtraction. So this shows the register-register form for the subtraction operation. Here we're going to say this WB minus WS, stick the result in the destination register WD. We need to be careful about this. The add operation is commutative, which means that this add instruction right here, WX plus WY result in a WC, is going to give the same result as this add instruction right here, WY plus WX into WZ. However, the same is not true for these two subtraction operations. In this example right here, this is going to be W0 minus W1, while this one right here is going to be W1 minus W0. So you need to be careful about the order of these two operands. Finally, just like the add, the subtract instruction has a byte form. So let's take a look at some examples. Here we're going to say W0 minus W1, put the result in W2. So W0 has 1AF3. W1 has 8B1A. We can subtract those two. We get this result, which we place in W2. Let's reverse the order of these operands. So this time we're going to say W1 minus W0. So W1 is 8B1A. W0 is 1AF3. We do subtraction. We get a different result than the previous example. So now we get 7027. That's written into W2. Here's the byte form of the subtraction instruction. Like all byte forms, only the least significant bytes of these registers are involved in the operation. When we produce this result, D9, that's going to get written into the least significant byte of W2. Its most significant byte is unchanged. A common operation that we like to do is either add or subtract a constant from a register. Here's one form that we can use to do that. Here we're going to add a 5-bit literal to a register and place the result in a destination register. Here we'll subtract this 5-bit literal from this register and place the result in a destination register. This is a 5-bit unsigned literal, which means it has a limited range. It can only represent numbers in the range of 0 to 31. So as examples, here's a word operation where I'm adding 4 to the W0 and placing the result in W2. Here's a byte subtraction in which I'm subtracting the value 8 from W1 and placing the result in W3. This add instruction right here would be illegal. This literal right here, which is 60, is too large. That's greater than 31. So this is an illegal form of this instruction. So I mentioned that this constant 60 was too large for this instruction. So how could we accomplish this? It's easy. We'd simply have to use two instructions. For example, I would do a move, the immediate value, 60, into a register. Let's pick W2. Then I would do add W0 W2, let's put the result in W1. This two instruction sequence would accomplish what this illegal instruction sequence would accomplish. In fact, I could always use this two instruction sequence to accomplish this. It'd simply be less efficient than using this form. In this class, we are never going to grade you on efficiency of your assembly language programs. We just want them to work. If you want to use this form, feel free. You simply have to remember that this immediate value has to be in the range of 0 to 31, but you could always use this two instruction sequence to add in a constant value to a register. The previous form of the add instruction was a 3-operand form. Let's take a look at a 2-operand form. This first form right here, add F, is going to take a value in data memory, add it to WREG, which is W0, and stick the result back in data memory. If I put the destination as WREG, then this form will take the value in data memory, add it to WREG, and stick the result back in WREG. There are two limitations on this form. One is that F is limited to the first 8,192 bytes of memory, and because this is a 2-operand form, one of the operands, either F in this case or WREG in this case, will be destroyed. Here's a couple of examples. Add memory location 1000. This is going to take the contents of memory location 1000, add it to W0, and place the result back in 1000. By putting WREG at the end, we can cause the result, instead of going into 1000, to go back to WREG. Here's the byte form of this instruction. Observe that this instruction, add the contents of location 1000 to WREG, which is W0 with the result placed back in 1000, can also be accomplished by this 3-instruction sequence, in which we move the contents of location 1000 to W1. We add W0 plus W1, place the result back in W1, and then move W1 into location 1000. This will take 3 instructions and an extra register. However, in this class, we're only concerned with the correctness of your assembly language and not the efficiency. So use whatever approach that you best understand. So let's take a look at a couple of examples. We're going to do a word operation in which we take the contents of location 1000, add that to WREG, and stick the result back in location 1000. So the word stored at location 1000 is 8BFA. The word stored in W0 is D0 through 8. The result is 5C32, which is written back to memory location 1000. So memory location 1000 is modified after the execution of this instruction. Let's now add a WREG as a destination to the end of this instruction. The addition will be the same, except the result will now go to register W0 instead of to memory location 1000. Let's look at a byte form of this instruction. This is going to be add.byte, the byte stored at location 1001, add the result to WREG, and stick the result back in location 1001. If we look at this memory as being 16 bits wide, the word stored at location 1000 is SFA8B. The byte stored at 1001 is going to be the most significant byte of the word stored at 1000. So that's going to be 8B. So we're going to add 8B to the lower byte of W0, which is going to be 38. The result, C3, is going to be written back to location 1001, which is the most significant byte of the word stored at location 1000. This slide shows the 2-operand form of the subtraction operation. This works in exactly the same way as the previously discussed add operation, except we're doing subtract. Here we're going to take the contents of data memory location F, subtract from that the contents of our working register, which is W0, and place the result back in the memory. Here, if we put the destination as WREG, the same operation is performed, except the result is going into WREG. Here are some examples. Here we're going to take the contents of memory location 1000, subtract from that the contents of WREG, which is W0, place the result back in 1000. Here, in this example, the result is going to, instead of going to 1000, it's going to go into the working register. A very common operation is the increment operation, in which we add 1 to a value. Here, this form is a register-to-register form in which we're going to take our WS, add 1 to it, and place the result into our destination register WD. Here are the data memory forms of this, in which we're going to take the contents of memory location F, add 1 to that, and stick the result back in that data memory location. In this case, the destination is going to be the working register instead of the memory location. We had the same limitation as with the add subtract forms of these instructions, in which F must be in the first 8,192 locations of data memory. So here's some examples here. Increment W2, W4. This is a word operation. We're going to take the 16-bit value in W2, add 1 to it, stick the result in W4. Here's a byte operation. We're going to take the least significant byte of W3, add 1 to it, and stick the result back in the least significant byte of W3. Here we're incrementing the contents of memory location 1000. It's a word operation. The result is placed back into location 1000. Here we've placed the, we've specified a destination as the working register, and we've also made this a byte operation. So this is going to end up, this is going to take the byte stored at location 1001, add 1 to it, and place the result in the least significant byte of WREG. This slide is the same as the previous slide, except we're using the decrement operation instead of the increment operation. We have a register-register form of the decrement, and we have our 2 data memory forms of the decrement operation as well. These examples here simply mirror the increment examples on the previous slide. So far we've concentrated on looking at instructions that modify the working registers, but there are other registers in the pic24. Recall that a very important register is the program counter. The program counter contains the program memory address of the instruction that will be loaded into the instruction register and eventually executed. At power up, the first instruction is going to be fetched from location 0. That means that the program counter is reset to 0 after power up. Recall that the number sequence computer had an instruction called jump. The operand was an address, and this address was loaded into the program counter whenever this instruction is executing, causing an unconditional jump to wherever instruction was located at this address. The equivalent instruction on the pic24 is a goto. We specify the operand as an expression that's going to be translated into an address that's going to be located into the program counter. This shows the encoding of the goto instruction. The goto instruction is one of the few instructions in the pic24 that takes 2 program memory words to encode. This NN field that's in these 2 words is going to be the upper 22 bits of this address. That's going to be concatenated with a 0, and it's going to form a 23-bit value that's going to be loaded into the PC. We only take the upper 22 bits of this address because we know that this address has to be even, which means that the lower bit, the least significant bit, is always a 0. A goto program memory location 800 is encoded as these 2 program memory words. A goto instruction is an unconditional jump. At this point, we've been a bit fuzzy about exactly what addressing modes are valid for instructions. So the definitive answer can be found in table 19-2 of the pic24 datasheet. This is the particular device we're talking about in this class, and actually these forms are valid for all pic24 devices. This table has an instruction mnemonic. It has the various forms of that instruction. It has the description of each form, has the number of instruction words that it takes for each instruction, the number of instruction cycles that it requires to execute each instruction, and the status flags that are affected. We'll talk about these 2 columns in a later lecture. We've already discussed about the instruction word encoding of some instructions. What I want to concentrate on in the next couple of slides is what these variable symbols mean in these instruction descriptions. So the register-to-register description of the move instruction says move WSO to WDO. What do these symbols mean and where are they defined? They're defined in table 19-1. Here's a partial list of them. So WSO is the source W register, and it can either be one of the 16 working registers here using the register direct form, or it can use one of these various register indirect forms. Register DO is a destination register. It can use register direct or one of these register indirect form. So these symbols are attempting to communicate the valid addressing modes for each of these operands. The app form uses WB for this operand, which is going to be one of the working registers, W0, W15. WS for the second operand, which can be one of the working registers, so using register direct or one of these register indirect modes. And also WD for the destination, which is going to be either register direct or one of these register indirect modes. Which means that this is a legal form because all of these support register direct. This is also legal because these two, WS and WD, support register indirect. However, this is an illegal instruction here because this indirect form here is not supported by this WB register here. So these tables and symbols are important in terms of telling you what addressing modes are legal for each operand. We do not expect you to memorize all these various addressing modes that are valid for these instructions. You will be provided this tabular information on a test. It also helps that the pic24 uses the same rules for instruction forms. For example, the sub instruction, which also has a 3 operand form, has the same general rule for these operands. We'll cover other instructions that also has 3 register operands, and they will use the same rules. Problem 27 says subtract .byte the value 10 from W4 and store the result at the register indirect location W0. So let's first of all do the computation. So we're going to look at W4. It's a byte operation, and we're going to take the least significant byte, which is going to be a 0x05, and we're going to subtract from that 10. This is a decimal 10, so let's write that in hex. So it's going to be 0a, and let's do the subtraction. So in doing the subtraction, we need to subtract 10 from 5. We got to borrow from out here 1. That's going to leave this an F. We're borrowing a 1 here is going to mean that this is going to be a 16. So 16 and 5 is going to be 21 minus 10. That's going to leave an 11. So this is going to be a B here. 0 from F is going to be F, so our result byte is going to be FB. Now, where is this result byte going to be written? It's going to be written to register indirect W0. So let's look at W0. We need to treat that because it's register indirect as containing an address. So this result byte of FB is going to be written to memory location 1006. So where's 1006? It's right here. And it's the least significant, where it's a byte operation, so 1006 is going to be this byte right here. So this memory location is going to change to, the upper byte will remain unchanged as E7, and 1006, the C0 byte, is going to be replaced with FB. So our final result is that 1006 is going to contain the value E7 FB when viewed as a 16-bit memory. Problem 29 has the instruction decrement 2.byte memory location 1008. This is going to subtract 2 from the byte value at location 1008 and place the result back at location 1008. The byte value sitting at location 1008 is a 0, 0. So the operation is going to be 0 minus 2. This is going to force us to borrow across the 0. It's going to leave this an F. Borrowing a 1 in here means that that's 16. So 16 minus 2 is going to be 14. That 14 is going to be an E in hex. 0 from F is going to be an F. So our byte result is going to be an FE. So the 0 here will change to an FE. The final 16-bit value stored here is going to be an FF, FE. Problem 31 has the instruction increment 2.byte memory location 1009. This is going to take the byte value stored at 1009, increment it by 2, and store the result back at 1009. So let's look at memory. The 16-bit value stored at 1008 is FF00. The most significant byte of this location is going to be 1009. So we're going to take an FF and we're going to add 2 to that. So this least significant byte is going to be 15 plus 2. That's going to be 17. That's greater or equal to the base, so we subtract the base from it, and we're going to leave a digit of 1 behind. So there's going to be a 1 here. We're going to have a carry of 1 to this column. 1 plus 15 is going to be 16. Subtract the base. That's going to leave a digit of 0 here with the carry of 1 out. So our final 8-bit result is going to be a 0, 1. So this upper byte FF will change to a 0, 1. So the final result of this 16-bit value is going to change to a 0, 1, 0, 0.